All right, so for today's lesson, we're going to be doing an introduction into logarithmic functions and their graphs. So a logarithmic function is an inverse of an exponential, and you can express any exponential function as a logarithmic function. And just like similarly, you can express any logarithmic function as an exponential function. And the reason that logarithms really came about in the first place is because they're really useful in helping us to use very large numbers or very small numbers with multiple decimals and manipulate those to make them more manageable, is essentially what logarithms are for. So a couple of key properties that you need to know is when you're looking at a logarithm, so the a value, so when I say a value, when I'm talking about my exponential function, so y equals a times b raised to x, that a value is the y-intercept. Y'all guys learned about that in your exponential review. That has to be greater than 0. You have to start somewhere. Your base, your b, has to be greater than 0 as well. And the base cannot equal 1 because 1 raised to anything will remain 1, and that's not what we want for an exponential. So what you need to know is that the conversion between the two. So if I have a exponential function, so we're just going to start with the basic exponential function that has the a value of 1. I can convert this. The base is always going to remain the same. So the base is the base in an exponential or in a logarithm. But what you do is you convert it so that, I know a lot of people like the loggy froggy face, but essentially what you're doing is you're going to switch your equal to and your exponent. So this now becomes log base b, and then my exponent was y. Okay, so my exponent was y, and my x was my equal to, and we're going to switch those. So this is now going to become raised to x equals y. Now, why is that important? Well, when we look at it in terms of an actual graph, okay, so I'm going to bring up Desmos so we can look at that. When we look at it in terms of a graph, we can see that they are inverses of each other. So I have y equals x, because remember, inverses are reflections over y equals x. And I'm going to start with y equals the exponential function 2 raised to x. So we're going to start with a very basic. So y equals 2 raised to x. So if I look at a table here, and I am going to do some point plotting just so you can see what we have. All right, so we have y equals x. There's my little reflection line. And for my exponential, so we know that our exponential, we have a point at 0, 1. We should have another point right here at 1, 2. And then we should have another point at 2, 4. So we have this exponential function here. So my logarithmic function is going to be the inverse of that. So remember, we just did the table. We did 0, 1, 1, 2, 2, 4. So if I inverse and make my logarithm, that's going to give me 1, 0, 2, 1, and 4, 2. So if I regraph that, I have 1, 0, 2, 1, and 4, 2. And we can see that it has that reflection over that y equals x, making it an inverse. All right, so a few key things. When you're looking at it graphically, we can see y equals, to put it into Desmos, you can actually type log using your keyboard. Right now I'm on my iPad, so I can't do that. But it's under the functions. And then if you go to the MICS, what stands for miscellaneous, you have 2 log options, and I'm going to explain the difference between the two. But for right now, we're going to use log where you actually tell what the base is. So we're going to use log base 2 of x, and there's that inverse that we were just talking about. Because remember, the base is the same regardless if it's an exponential form or logarithmic form, okay? So let's talk about some properties, and we will come back to some more about the bases. So these properties are valid whether we use base 10 or base e, and I'm going to explain what those mean in a little bit. But if I have a logarithm and I have a base and it's raised to a power of 1, it equals 0. Well, why is that true? Well, I'm going to convert it back to exponential form. So start with the base, 0 to 1. So there's that loggy froggy face. I don't know if you've heard that before, but it gives you the order that you would put everything together. So base raised to 0, because that would be the next stop, equals 1. Well, anything raised to a power of 0 always equals 1. So that's why that's a true statement. All right, so then the next one. If I have the same base, so this is a very important, if I have the same base and the same raised to value, then it will always equal 1. So again, if I convert it over, I have my base raised to 1 equals b. Well, that is a true statement because b raised to the first power is equal to b. All right, so if I have b raised to some other exponent, so if I have a power on top of a exponent, that is going to equal that power. So the base raised to y equals this whole thing. So b raised to y equals b raised to y. So it equals the y value. Okay. And finally, if I do the backwards option of that, if I have the base raised to a logarithm that has the same base, then it's just going to equal, and that should be equal to right there, it's going to equal x. Okay, so a lot of these properties you're going to see form out when you're doing them, but these are definitely 4 shortcuts that you can remember. If you know it's raised to 1, it's equal to 0. If it's got the same base and same exponent, it's equal to 1. If I have the same base and same exponent raised to a power, then it's equal to the power. And then, of course, if I have the same base and a logarithm raised to that, then it equals the exponent as well. So we have 2 different types of logarithms that come up very often. One is the common logarithm. So the common logarithm was developed using a base of 10. So just like if I have the variable x, I know that it's automatically got a 1 in front. The same thing happens when I have a logarithm. If I have a logarithm and I don't see a base down here at the bottom, then I know it's an automatic 10. Okay? So common logarithm has a base of 10. Where did that come from? Well, it came from scientific notation. So when we talk about scientific notation and I have a power raised, power of 10 raised to -3, that means I'm going to move my decimal place over 3. Or if I have a positive, then I'm going to move it to the other direction. So remember me saying that logarithms were meant to help us use really big numbers or really small numbers in more manageable fashion. So you're going to make sure that if you do not see a base, you know it's 10. Now, we also have what we call the natural logarithm. So every exponent, okay, so when we talk about exponential functions, we have what we call the natural base e. E is an irrational number, just like pi is an irrational number. So if I have log base e raised to x, we don't write log base e raised to x. We actually write the natural log using the notation ln. And you can actually find that in Desmos as well. So this is the logarithm, the common logarithm. You see that it doesn't have the base, so we know it's 10. Okay. We have the natural logarithm with a notation ln. And then we have the logarithm where we have a different base other than 10 or e. Okay. So we're going to practice converting back and forth between the 2 forms. So if we have a logarithm, we want to convert to exponential form. So remember, the base is the same. All right, so my base in this particular problem, so I'm going to zoom in here, is 4. So my base remains the same. What you're going to flip is your exponent and your equal to. So when I convert, whether you're converting to exponential form or whether you're converting to logarithmic form, your base stays the same. So my base is 4. My new exponent is going to be 10. And my equal to is going to be k. So again, if you like the loggy froggy, you start with 4 raised to 10 equals k. And you can actually figure out what k equals. You could say 4 raised to 10, and now we know that k equals that value. Now, for the next problem, it says ln. So you need to rewrite this so that you know that this has got a natural base e. So when we convert this over, my base is still going to be the same. So my base is e, and I'm going to switch my 9 and my 2, my exponent and my equal to. So e raised to 2 equals 9. And that is not a true statement, but for right now, we are just converting things over. So when I look at my loggy froggy, I can say e raised to 2 equals 9. All right, so for C, I don't see a base here, so I'm going to automatically understand that there's a base of 10. So my base is 10. My exponent is going to be 0.5 raised to 4. So again, 10 raised to 0.5 equals 4. Now, what happens if I have something crazy like this that has this really long expression as my exponent? That doesn't change anything. We're still going to take my base as 9, raise it to 3, but we're going to set it equal to that whole thing, okay? So this is going to be 9 raised to 3 equals that whole exponent, and that whole exponent was x squared plus 5x plus 17. You'll see these on Desmos or on Delta Math when they ask you to convert. All right, so how do I convert to logarithmic form? Same process. The only difference is you're going to put a log as your notation this time. So my base for this one is 10. So my base is going to be 10 when I do my logarithm. So we're going to do log base 10, and we're going to switch our exponent and our equal to. So my exponent in the original is 2, so that's going to become my equal to, and my equal to becomes my exponent. So 10 raised to 100 equals 2. So the loggy froggy was just backwards this time. Again, my base is 3. So 3 raised to 81 equals 4. So the process, again, is the same, just time, except for we're adding logs. So log base 3 raised to 81 equals 4. Now, I will go back to this letter A, and if you actually convert this over, you don't necessarily have to write the base of 10, because it's a common logarithm, and we know that that 10 doesn't have to be there. And this last one. So my base here is n raised to w equals y. So log base n raised to w equals y. And the last thing is, can you use your calculator to actually calculate some of these logarithms? And you have to make sure you're using the right one. So A is a common logarithm. So we're going to do logarithm of 34.5. If I can type it correctly. All right, so we get approximately 1.5378. Okay, so normally with logarithms, I like at least 3 to 4 decimal places, especially when you're using them to find answers later. All right, so we know that B is also a common logarithm, so we're going to make sure that we use the common logarithm, so -3. And we see that that is undefined. Well, why is that undefined? Well, it's undefined because we can't have that negative exponent here, okay? So when you have a logarithm, it can never equal a negative exponent. So keep that in mind for the future. All right, and then if you know your properties, then this log of e stands for the natural logarithm, ln, raised to e equals 5. Now, one of the properties that we talked about said that if I have the same base and the same exponent, then it automatically will equal what it's raised to. So if I have these two, that's going to cancel out, and it's going to wind up equaling 5. Again, I can type that into my calculator though. So the ln of e, so e is located, I think you actually use the keyboard for this one, if I remember correctly. You just use E and it automatically knows. And we're going to raise that to 5. And we see that that equals 5 as well. And then, of course, the natural logarithm of -5. So the natural logarithm of -5 is also going to be undefined because it still has that negative exponent value, because this is log base e raised to -5. We can't have that -5 as our exponent value. So that is going to be undefined. So keep that in mind, because when we start solving, that's going to be super important. All right, so for today's lesson, we talked about what a logarithm is. So a logarithm is an inverse of an exponential and is again, exponential, logarithm, we can write them back and forth between the two. So we learned how to convert over. We learned that a common logarithm has a base of 10, a natural log has a base of e, and we also learned how to use the correct notation